Asteroid struck by a spacecraft might be healing as its surface reforms. And this is a stereoscopic movie generated from the team's simulation showing the first 30 minutes after the impact. Smacking a spacecraft into an asteroid may have had some interesting side effects, according to an analysis of a collision between NASA's DART probe and the asteroid Dimorphos back in September 2022. The tiny asteroid shape could have changed significantly as a direct result of the impact, and this offers some clues about how the asteroid formed in the first place, while also suggesting the upcoming mission to investigate Dimorphos will find not an impact crater, but a neatly reformed pile of space rock. The DART mission, Double Asteroid Redirect Test, DART for short, was one of the planetary safety. Scientists wanted to see if they could divert the course of an asteroid by ramming it with a spacecraft. Dimorphos was the chosen target. It was a small asteroid in a mutual orbit with a larger binary companion called Dimorphos. And because the orbital period of the binary object was well known, any changes in the timing of its period would mean that the mission was successful. And a success it was. The impact had a much greater effect on the timing of the period than scientists expected, but the DART mission was the first time humanity had ever tried such a thing. We didn't know if there would be an ongoing effect to observe and what those effects might be, what they could mean for asteroid redirection, and what, if anything, they would tell us about Dimorphos. Obviously, scientists have been monitoring the space rock for changes, but a team led by the planetary scientist Sabina Raducan of the University of Bern in Switzerland took a different approach. They took a simulated Dimorphos and a simulated DART spacecraft and tried to replicate the observed effects of the impact. And that includes the transferal of momentum from the spacecraft to the asteroid, the amount of material that erupted from Dimorphos, and the shape that material formed as it spewed into space, known as the ejectacone. To do this, they needed to tweak unknown variables, the composition and density of Dimorphos. Not all asteroids are built alike. Some are more dense, such as the chunks of planets arrested in their development by large impacts and broken up into smaller fragments. And some are what are known as rubble piles, which is pretty much what it sounds like, looser agglomerates of dust and pebbles that have come together, but would be more susceptible to coming apart under gravitational stress, for example. We already knew that both Dimorphos and Dimorphos fall into the rubble pile category, but the DART impact can tell us exactly what Dimorphos is made of. Raducan and her colleagues were able to produce simultaneous simulations consistent with the observed result of the DART project, and in these simulations, the asteroid is held together so loosely that DART did not even leave a scar on the surface. Instead, the spacecraft caused global deformation and resurfacing. For this to occur, the asteroid needs to be very weak rubble pile. Its cohesive strength, the team's calculation suggests, is less than a few pascals. This is very similar to asteroids Ryugu and Bennu, both of which have been visited by human spacecraft for data and sample collection. The simulations also suggest that the density of Dimorphos is very low, around 2.4 grams per cubic centimeter. That's slightly denser than Ryugu and Bennu, which sits around 1.28, 1.26 grams per cubic centimeter, respectively. The density of Earth, for context, is 5.51 grams per cubic centimeter. The boulder density of the simulated Dimorphos was consistent with the density obtained from DART observations. And these findings suggest that Dimorphos may be Didymos' asteroid baby. But Didymos is also a rubble pile, and we know that rubble piles often shed debris as they spin. And thanks to centrifugal force, some of this shed debris remains in orbit with Didymos, according to the model of Dimorphos formation. Over time, it clumped together to become a loose rubble pile we walloped up with a spaceship. And we don't know if they're right, not yet, but we will. Later this year, the European Space Agency is launching the Hera mission to study Didymos and Dimorphos. If what Hera finds is consistent with the team simulation, we'll know a lot more about Dimorphos than we did. And this has implications, not just for our understanding of the ongoing evolution of the binary, but asteroids, asteroid binaries, and how we plan and execute an upcoming asteroid redirect missions. Since the DART spacecraft probably caused global deformation of Dimorphos, we can infer that similarly formed asteroid moons are easily reshaped and their surfaces are relatively young, the researchers write in their paper. Overall, the findings of this study provide valuable information for understanding the formation and characteristics of binary asteroids and will inform future exploration and asteroid deflection efforts. The research was published in Nature Astronomy, and this is on Science Alert by Michelle Starr. Please leave your comments, and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.